fetch macro state to the particular instruction sequence, micro sequence. How do we do that? Chris? How do we do that? It's sort of building on what you learned about branch unequal, right? In branch unequal also you had a similar situation that you either had to continue with the without modifying the PC, meaning that you go to the sequential path of the program, or you may have to take a branch, right? And in either case you have to come back and join the fetch macro sequence, and we did that in BEQ, right? How did we do that in BEQ? How did we do that in BEQ, Abhishek? How did we we had to go from two different paths back to the fetch. The normal path is you complete the sequence, don't modify the PC, just go back to fetch. The other one is you modify the PC and use a modified PC to go back to fetch. So there were two different ways in which we had to effect that, and remember that these sequences are static, right? The micro sequences are static. You cannot change the sequence itself. The code is burned into read-only memory, and so we were using some magic in order to make that happen. So how did we do that? Remember, how did we do that in BEQ? I'll give you a picture. So Z-bit, right? So Z-bit, using the Z-bit, we were able to say that go to one of two different places, and normal fetch macro state, the address may be something, so the normal fetch macro state, what we would do is this is the path by which Z is 0, and what you're going to do is you have to go back to a clone of the fetch state, right? So because fetch state is nothing but a sequence of bits that is stored in ROM, and I can take that same set of bits and put it into a different ROM location, and so long as I go to that address, the effect on the data path will be exactly the same, right? So we are generating the same control signals from the ROM, and that's what we did. We cloned this, right? And this is how we implemented a two-way branch, right? So here we have a two-way branch. The first branch is, this branch is saying if branch this particular instruction, branch unequal instruction, if the equality fails, right, then you simply go back to fetch, right? On the other hand, if the equality is successful, then you modify the PC, and then you're going to go back to fetch, right? So these are two different things that we were doing, and we're basically able to effect the two-way micro branch. Now there's a macro branch. There's a macro branch that is happening at your program level, which is a BEQ instruction, and there's a micro branch that is happening in your sequence, and we were able to effect that by taking the dynamic state of the Z-bit, right? The Z-bit has been computed in this state, and it is containing the result of the arithmetic that you did in the BEQ instruction, and so you're using the result of that arithmetic in order to make the decision where to go. Is that? So Zoe is a fantastic question, and that is, now we are saying Z-bit is going to be part of the address into a ROM, right? And so what you have to make sure is, the only time that it really comes into play is when Z is 1, right? When Z is 0, it's a normal thing. So you can think of the ROM being divided into two halves. One half is when Z is 0, and that's the normal sequence of instructions. And Z equal to 1, then you have it's going to take you to a different portion of the ROM, and all of those portions are irrelevant to us, right? There are only few locations in that is relevant to us when we explicitly set the Z-bit to 1 in our data path. Is that idea clear? No, it's not a 0 onto the bus. Remember that the output of this is coming from the data path in a particular register called the Z register, and we are clocking the register only when we need it, right? Only in the BEQ instruction we are clocking the register, otherwise we are never clocking it, and therefore the output of the Z register is always 0, right? It's guaranteed to be 0 except when we explicitly clock it using the load Z bit, right? And therefore what you're doing is you asked an excellent question. That is, we are wasting a significant number of ROM locations for all the times that that z is going to be 1 when you don't need it, when we don't z is 0 when we don't need it. Okay, so we'll come back to that in a minute on how we can control that. But is this idea clear that how we are doing this micro branch? Okay, so now tell me how we can do the decode microstate, macro state. So here we want to do a similar thing, except that there's a micro branch that is taking us to several different places, not just 2 places, right? So from the last fetch microstate of the fetch macro state, what we want to do is we want to go to one of several different locations. How can we do that? What information is available to you that will help you make the decision? Just like the z bit was there is something that's available at the end of this fetch macro state that can help you in making this micro branch. Alex, PC offset. Chris, the opcode. Remember, at the end of the fetch macro state, we've got the instruction register. The instruction register has the opcode, right? And so since the opcode is there, that's the dynamic state that we're looking for, just like the z bit. That's the dynamic state that we're looking for. Now we can use that opcode as a way of effecting a multi-way branch, right? So we can say that there is a base address, and then there is the opcode that is prefixed. Just like, if you have an address, a street address, I'm a postman. First thing that I'm looking at is the street address, right? So I'm going to Blue Spruce Trail. That's the road that I want to get to. Then I say, well, what is the number that I want within that, right? So similarly, what you can do is you can have a base address specified statically in the fetch microstate. The base address is go to execution sequence, okay? And the base address can be something like 1000, let's say. Okay, that's the base address. And what we're going to do is we're going to modify the first 4 bits of the base address by the specific opcode that is coming from the instruction register, right? So if it's an add instruction, it's going to be all zeros. If it's an AND instruction, it's going to be 0001. So that's the prefix to the static address that is in the fetch microstate. Is that clear? Idea clear? Any questions on that? This is key for how you will implement your project one itself, right? So make sure that you understand how this works. Okay. So once I have that, then I can simply go to any number of these sequences. And once I go in here, then I can go sequentially through the micro sequence, because here it is static determination what has to happen in the add 1 microstate, add 2 microstate, and so on till I finish the add micro sequence and then go back to fetch again. Everybody with me here on this? Okay. That's a very simple trick. And so once you have this, then I can implement this multi-way branch. Okay. Okay. And so now we can go back to all the drive signals that we have, and the load signals that we have, and the micro in the ROM, the write signals that we have. And so these are all the static signals that in every microstate you decide that if I'm an add 1 microstate, I want certain drive signals to be on, certain load signals to be on, certain write signals to be on. So these are all static things that you decide, and you also say what is the next state that you want to go in a particular microstate, right? But now what we've done is we've also added 2 additional modifier bits, right? And the modifier bits are going to come into effect exactly when Zerb is talking about. That is, we're not going to use it always, right? So we're saying under certain, when we want it to be modified, for instance, the last microstate of the fetch sequence, I'll have the modifier bit turned on to say that, well, modify the top portion of the micro ROM address using the opcode bits. And similarly, in the last, in the BEQ3 state of the branch sequence, you will say that turn on this modifier bit to indicate that I want to do a 2-way branch, taking into account what the value of the z bit is. So that's the additional thing that we've added to the microcontroller. And so now if you look at the control unit, we've got the ROM, which contains all of the microcode that you've written, and you have the state register that is saying what is the next state you want to go to. And these are all the static signals coming from a particular ROM location. From that particular ROM location, you're driving the data path using the drive signals, using the load signals, and the function that has to be supplied to the ALU, and the register selection. All these kinds of things go out from the ROM, and the additional things that go back into the control unit is the M and T bits, right, which are the modifier bits, and then the modifier circuitry takes on these 2 bits along with the opcode bit, opcode 4 bits, and the Z bit register, and then decides whether it wants to modify the top 5 bits of the address or not, right? If it is not required, then it doesn't modify it. If it is required, it is going to modify it. Is that idea clear? Okay, and so this is a circuitry that's pretty simple to think about in design, and if you notice in our project, we have 2 versions of project 1. One is a simple version building on what Zoe was asking earlier, which is going to use redundancy. We're going to waste a lot of space, right? Because when the modifier is all zeros, then there's a portion of ROM that we never, modifier is all 1, let's say, in a different combinations of, well, actually, let me back up. When the modifier is all, make sure that the top address bits are 0, then we're using 1/2 of the ROM. That's the normal unmodified portion, static portion of the ROM. Okay, and the dynamic portion of the ROM is when you have to make these micro branches, which happens at the end of the fetch macro state, or at the end of, or in the middle of the branch instruction, right? And during those conditions, then we are having some of these bits being not 0, right? Which means some portion of the ROM we're going to use, but there's a large portion of the ROM that we're never going to use. So there's a space that we are wasting in the ROM when we do this. And one thing that you can do is actually build what is called a micro sequencer that reduces that space complexity. And so in the project, there are 2 versions of it. The base version that I expect you to implement is, don't worry about wasting space, right? So first we want to get it right, okay? And so in order to get it right, just do it the vanilla way, which is using a simple circuitry for modifying the top 5 address bits when you need it, and not worry about the fact that you're using space in the ROM when you don't need it, right? But on the other hand, there is a second part in project 1, which is actually saying, if you build a micro sequencer, then we can actually reduce the space complexity of the ROM, and that is an optional part of the project. You get a bonus 10 points if you do that, okay? But it is not expected that you have to do that. Any questions on this? How the control unit works? I didn't see last Thursday's lecture, so I'm assuming that you're all now completely familiar with how to write the sequences and so on, and we are sort of wrapping up that discussion. Any questions? Yeah, Shane. Mm-hmm. No, opcode is 4 bits. Yeah. Well, so there are 4 bits. Am I not right? 3 bits. Well, in the project one, you're right. Right. In the project one, there's a limited set of instructions, but in the 32-bit architecture that the book talks about, that's why I told you that you have to sort of keep that dichotomy, right? So what we're discussing is the full-blown 32-bit architecture that is discussed in the book, and that has 32. In the 32 bits, the top 4 bits are reserved for the opcode. Yeah. Okay. All right. Any other questions? Okay. So the last thing that I want to mention is that this style of circuitry that we've been a control unit design that we've been talking about is what is called a microprogram control unit, right? Because what we are doing is, you all understand your assembly language program, which gets converted to a machine language program, is a macro program, right? That is happening at the level of the instruction set that has been made visible to you. But you as architects implementing the processor, you're going one level down, and you're implementing what are called the micro sequences, and that is microprogramming. So what you're doing is you're programming the hardware directly, right? Because essentially all these control signals that you're generating is nothing but orchestrating what is happening in the control unit in every clock cycle for which you've written a program which is sitting in this read-only memory, and that is what is called a microprogram. Okay? And one nice property of the microprogram control is that all of the control is residing inside this ROM, right? So all the sequences, you basically boiled it down to ones and zeros, and you have stuffed it into this ROM, and that is how you're controlling the entire data path. So if something goes wrong, if you have to debug it, what you have to do is you have to see what signals are being generated in one particular micro instruction and see if that is exactly the signals you want, right? So in terms of maintaining such a design, it's much easier because it is all contained in this ROM, and you program that ROM. So you can actually write that program, and then you can have a microassembler that takes that program and then converts it into bits that you can store into this ROM, right? Now another way of doing that, doing the same design is using random logic, and you know that you've all done combinational logic and sequential logic design, and a logic function is represented as a function. It's a function of a whole bunch of inputs, right? So this is a logic function, and an example of such a logic function would be, let's say, drive PC is one logic output that I want to get out of this control unit. Now, if I wanted to implement drive PC as a logic function, I can say what are all the states in which I need drive PC. I can go through my sequence and see that, oh, when I'm in fetch state, I fetch 1, I need the function to be this drive PC to be on, and perhaps in I fetch 2, I want it to be on, and so on. Some BEQ state I want it to be on. So this is basically a logic equation, right? There's a logic equation, and you can implement this using and or logic, right? So this is what is called sum of product form, right? You've heard of this term, sum of product form. It is a sum of individual logic functions. Each one of them may be a product. In this case it is I fetch 1, but it could be more than that, more variables in this particular term. So it is a sum of product form, and you can implement this as a bunch of gates, right? So as a bunch of gates like this, and this is the output that you want to generate, and you have as many of these AND terms as the number of individual terms that you see in this equation, and the number of OR inputs is the number of things that you are ORing together in order to generate this particular logic function. So in that sense, you can take each one of those guys, right, each one of those output that you see, and go back to your sequence and say, well, what is the logic function that is represented by that, and create a logic function, logic gate, a combination logic circuitry that implements each one of those functions, right? And this kind of design is what is called a random logic design. Or it's also called hardwired design. Hardwired design. Why is it called hardwired design? Why is it called hardwired design? Any idea? Brad, right? Brad? Shashank? Right, so you're wiring these things together, right? And you wired it, and that's it. You've frozen it, right? Afterward, if you want to change it, you have to go and remove some gates. Suppose you made a mistake in your logic design, right? You have to go and cut these wires and reconnect different wires in order to correct the design flaw that you may have in your particular implementation, right? On the other hand, if you look at this design, the microprogram design, the nice thing is if there is a flaw, then it is just particular line or a location in your micro ROM that happens to have the wrong selection of bits. You can go and modify that, right? And so you can reprogram the ROM in order to correct any design flaws. Whereas in this case, it is harder to. In this case, it is harder to do, and that's why it's called hardwired design, and this is called microprogram design. Drew. It's a sum of product, right? So it is basically what you're doing is each one of these is a product term. So I've shown this to be I fetch 1, an arbitrary logic function, if you have a logic function which is a function of say f1 is a function of a, b, and c, f1 may actually be a times b plus b times c plus a times c plus etc. Right? So this is what is called a sum of product function, and so each one is an AND gate, and you have an OR gate that is summing it all up, right? And so every one of these control signals that you have to generate for your data path, you can represent it as a sum of product form, and you can implement it using combination logic circuit. Okay, so this is one way of doing it, and so there is this dichotomy or alternatives that's available to you in terms of implementation as either a microprogram control or a hardwired control, and it turns out that there are new things that are available in the market. You've all heard of FPGAs. Heard of FPGA? Anyone? Matt. Okay, what is it? Okay, Nate. Okay, so that's another thought. Michael, right? Right? Yeah. Right. Is it a board? Is it a chip? What is it? It's a chip, right? It's a chip, and just like we said, RAM is one memory chip. Similarly, an FPGA is a chip. Okay, as opposed to memory, what it has is gates, and gates are just AND gates and OR gates and things like that. And so this is one example of it where I'm showing AND plane and OR plane, right? And so you have a whole bunch of these gates, and what you can do, as Michael pointed out, you can program it on the fly, right? So you can program it on the fly, and so now one of the nice things is that earlier I said these are discrete logic gates, and this is resulting in a random logic design, hardwired design, hard to debug, and so on. But now what I'm saying is all of that can be put inside a single chip and can be programmed, field programmed, and which means that it is much simpler in terms of maintenance. Just as microprogram was simple to maintain, this is also becoming easier to maintain once you adopt this technology of FPGA. And so the sort of relative advantage of microprogram design versus this hardware design has shrunk because of the fact that now you have this ability to freeze all of your hardware into a field programmable gate array, and you can program it, and therefore you can modify it. Okay, if things go wrong, you can modify it, and that's one of the nice things is about this design. And so that sort of relative advantage between the two is shrunk a little bit. But can you think of any other reason why FPGA may be more efficient than microprogram design? Mikey, who's Mikey, right? Okay. What's your name? Yeah, Ryan. Any other reason that you can? I gave you one reason that microprogram could have been easier, that because it is all freezing it into locations that you can actually inspect and then change on the fly. But any other reason why, say, FPGA or the hardware design may be better than a microprogram design? Well, you have a point there, but I wanted to be more specific than that. So let's try Peter. Hardwired could be higher performance. Why is that? Right. So usually when you say memory, there's an access time involved, right? And so in principle, you are doing an access, memory access, in order to pull out the control bits and then send it to the data path, and therefore there could be a disadvantage. But there are ways of getting around that. You can prefetch. You can sort of look ahead and know what is the next instruction that you want to pull out, and so you can actually start pulling it out. There are ways in which you can shrink that slight disadvantage that you might have. Any other thoughts? Zob actually asked me a question. So the answer to my question lies in the question that Zob asked early in the class. What is the question you asked me? well, you talked about the Z bit, but elaborate on that. So think about the contents of the ROM. What is the contents of the ROM is having all of the control signals, right? All those control signals needed in every clock cycle. Only a few of those are required, right? What you're doing is there's an enormous wastage of bits because your the word width of your ROM is as big as the number of control signals that you need in the entire data path. And most of those control signals, if you start writing the sequence, you'll see that most of them are 0, right? So it's only a few of them that are ones. And one of the nice things about, so this goes back to what Ryan was saying about the hardware resources. So what we're doing is we're using a whole bunch of hardware resources to store zeros, which we don't really need. And one of the nice things about the hardwired design is that it is exactly having the number of gates needed to represent this particular function, right? And so it is more compact in design, and actually goes back to what Peter was saying about the speed advantage. When you have a compact design, it also results in higher performance. Okay, so these are all sort of relative advantages of FPGAs and microprogram design. You can see more of this in the book, and here is a quick summary of all of the points that we just discussed. And you'll see that both these control regimes, microprogram and hardwired, are still being used in modern processors. When you have very simple instructions, it is easier to implement it using a hardwired control. But if you have a very complex instruction which goes through several different microstates, then the chances of going wrong in your design is more, and therefore microprogram design is used for some complex instruction in the x86 architecture. Okay, so that's concluding chapter 3. Any questions on this before we move on? Okay, so you're all well set for doing your project 1? Okay, good. So let's switch gears now, and I'm going to do a PRS, and then we will. So what we can do is, where is Drew? Drew, you want to have the break right now? Or do the PRS and take the break? Okay, so let's do the PRS, and it's on channel 5 if you want to tune to that. Shall we get started? All right, so Chandler, did you have a question? Oh, okay. Okay, all right. So that's question 1. I think most of you got it right. So if you, some of you think that it is always done by the caller. We know that that's not true. If you attended the class, you would know that. So let's go to the next one. Okay, so most of you have the right answer. That's good. Um, some compilers as an optimization may put it on registers, but usually the first pass it's always done in the stack, and you might optimize it later on. So when we say usually, it is kept in the stack. Okay. Go to the next one. All right, so most of you have the right answer. So we know that you have multiple activation record on your stack, depending on the nesting level of the procedures, and so it is always the frame pointer is a convenient way of making it point to a specific location on the stack, and that's the right answer. So you all know about this activation record and a particular location on the stack, which is pointed to the harness for the frame to the stack, which is the frame pointer. Okay, so let's go to the next one. Hey, so I'm happy to see that most of you have the right answer. So basically, we talked about the fact that a clock, a register acts like a wall, right? So it needs one clock cycle to pass that wall. So you need one clock cycle to go from here to here, one clock cycle, second clock cycle to go from here to here, third clock cycle to go from here to here. So you need 3 clock cycles, which is answer number 4 here. Okay, let's go to the next one. All right, so most of you have the right answer. So basically, the number of state rows in the state transition table is saying what is happening in the current state, what is the input, and what is the next state, and that is the number of transition arrows that you see here. So you have 4 transition arrows, and those are the number of state transitions entries that you're going to see in that table. So the right answer is 3 here, choice number 3, which is 4. Entries in the table. Okay, let's go to the next one. All right, so most of you have the right answer. So we saw in the sequence also that the first 3 states of BEQ is common, and then if the operands turn out to be equal, that's when you have to do the calculation to see what the target of the branch is going to be. So it's only done if the operands are the same, and that's choice number 2 here. this question will answer to this question. If you're able to answer it right, then means you've been paying attention to the class, first half of the class. Okay, well, I'm surprised about this here. We talked about this in the first half of the class, and we know that the output of the z bit that is coming to the control ROM cannot always be 0. Then you cannot implement the two-way branch that we're talking about, and so it has to be something that that is dynamically computed, and that is the output of the z register in the data path. Okay, so the right answer is 3 here. Okay, I think that's all I have today. Yeah. Okay, so let's take a short break. We'll reconvene in 5 minutes. Okay. So when we talked about instruction set design, we saw the sort of interrelationship between compiler and the architecture, right? So that was much more evident, and there wasn't a lot of discussion on operating system at that point. And now when we talk about interrupts, you'll see that there is a strong interrelationship between operating system and the architecture and the hardware. And in particular, what happens is that, when I say interrupt, what does it mean to you, from the point of view of processor? What does it mean to you? What is your name? Chen? Jen? Okay, okay. And when does that happen? When, you're absolutely right. Jen says that, instructions are being executed by the processor, and you're deviating from that ordered execution of instructions. So when does it happen? Taylor? Keyboard, so that is an external event, right? An external event like pressing the keyboard or moving the mouse, that's an external event, and that is telling the program to stop doing whatever it's doing and do something else, right? So that is an external event. It's an interrupt. Any other reason, any other example that you can think of? Mike, I want to say Michael, right? Michael? Any other? Oh, what is something? What could go wrong? What could go wrong in your program? Divide by 0, right? So there's an example. So you screwed up, and so your program barfs, and that's an internal error, and that's also deviating from the normal execution, right? And that is what is called an exception, right? An exception is something that happens when you're doing something that is different from the intended program execution. Shane, you had another example? So is there any other example? Michael, sorry, yeah. Overflow is also, is that different from, it is different semantically from divide by 0, right? But it is also an example of something that is unplanned for, that is happening in your program, right? You do not expect the overflow to happen. So it is a programmer generated error or exception. And so those are similar. Anything else that you can think of? Abhishek, did you have? More space. Okay, so I think you're on the right track. So let's elaborate on that. So what do you mean by that? So you are saying dynamically you want to allocate memory, right? So what actually happens in the program when you do that? Pardon me? Yeah. So when you say you go to the heap, who are you going to? Yeah. Who is going to that? So it's a system call, right? So in other words, you have a program. So let's say you write a simple program, hello world, right? It will take you 4 lines of C code to write the program, right? But is that all that program has? When you look at the executable, what is it going to have? A hello world program, okay? It's 4 lines of code, but in that you're going to have a statement that says printf, right, and that is going to print to the device. And did you write the printf routine? You did not write it, right? And so somebody else wrote that and you linked it in, right? So there is more to it than your own program. And so when you do that, what has to happen is essentially you're making a subroutine call, right? To printf, you're making a subroutine call, but you didn't write that program yourself, and the compiler during the linking phase is combining these different programs together, and if it is an operating system utility, like you said, the dynamic memory allocation, then the compiler has no way of knowing where exactly that piece of code is in the operating system, right? And so what the compiler is going to do is, in those places, it is basically going to have an instruction that says, I don't know what to do, right? It's what is called a trap. Okay, a trap is another internal exception, internally generated discontinuity in the program that is not an error, hopefully, right? It's not an error, but it is saying that I need some service and I don't know where that service is in the operating system. So it could be additional memory that I want, or I want to open a file, right? If I want to open a file, then again I'm going to the operating system and saying, get me this file for me, right? So that piece of code is somewhere in the operating system, the compiler doesn't know it, it basically sticks in a trap instruction that says, go to the operating system and then find out where exactly that piece of code is. Because we know that, like Jim said, the only thing that the processor can do is execute instructions, right? So it has to execute a different set of instructions, and that's what is going on with interrupts. So there are three types of interrupts, three types of, I'll call it program discontinuity, okay? Program discontinuity, going away from what you're doing normally. One type of program discontinuity is the external interrupt that Taylor pointed out. Okay. Second type is what Michael pointed out, which is and Shane pointed out, the program discontinuity that occurs because of your error in writing the program. You have an overflow, underflow, or a divide by zero. All these kinds of things result in program discontinuity. And the third type is where you're asking for a service that is in the operating system, and therefore you trap into the operating system. So it is called a trap because it's like opening a trap door and then falling in, right? You're executing your program and then suddenly you open a trap door and then you fall into the operating system, and the operating system says, okay, I caught you and I know what you want, I'll give it to you, and you'll resume the execution after that service is done. So that is called a trap. So these are three different kinds of program discontinuities, and there are synchronous events and asynchronous events. So these discontinuities can be either synchronous or asynchronous. Of the three that I mentioned, what are synchronous discontinuities? What is an example of a synchronous discontinuity? Peter? Right. So, but what do you understand? So you're right. You said that a trap is an example of a synchronous discontinuity, right? Now, why do you call it a synchronous? What do you understand by the term synchronous? Okay, so we'll come back to that definition a little bit more. What is an example of an asynchronous discontinuity? What is an example of an asynchronous discontinuity? I want to get your name. You're Tim, right? Okay, so what is your name? Jonathan, right, Jonathan. What is an example of an asynchronous discontinuity? Of the three that we mentioned, right? Is an exception asynchronous? It's not, right? So similar to what Peter said, it is you know exactly where it is going to happen, because you know the data flow, and you know that if you have an operand that's 0 and you're going to divide by 0, when you hit that instruction, you are going to get that, right? And so Brian, sorry. Yeah, so anything that you do if you hit the keyboard or the mouse, the program is not expecting that, right? So it is executing some set of instructions, and suddenly you have an external event that is causing that program to discontinue what it is doing and do something else, right? So interrupts are always asynchronous events, right? And so that gives you an idea, and you can sort of think of real life analogies for that. I mean, if you are working on your homework and you decide to go and get a soda, is that a synchronous event? That's a synchronous event because you decided to do it, right? So it is your own decision in the sequence that you decided to go and attend to that. Okay. On the other hand, suppose you're working on your program, on your homework, and your roommate comes and gives you a soda. That's an asynchronous event. May never happen, but if it happens, it's an asynchronous event, right? So you can see that synchronous event is something that you know is going to happen at some well-defined point. Okay, and that's what Peter was saying earlier, and that is, if you look at the program, and if you have a particular point in your program where I'm going to say open a file, you know that during the execution of that program, at that point you are going to have a trap, right? That's a synchronous event, and it is tied with the execution of the processor clock cycle. Okay, and similarly, if you have an instruction that is doing a divide by 0, you know that when you hit that instruction, you're going to have an exception, right? That's a synchronous event. On the other hand, if I hit a keyboard while a program is executing, that's an asynchronous event. It was unplanned for, right? And so is that idea clear? So in your micro sequence, for instance, when you're writing the microcode for the project, every state going from one state to another, is that a synchronous event? That's a synchronous event. All of the micro sequences that you write are synchronous event. Even if you take a multi-way branch, they're all synchronous events because it is all tuned to the clock edge, right? On a particular clock edge, you're going to the next microstate, and you're generating a bunch of control signals, and you're going to the next microstate, and so on. So that's the difference between synchronous and asynchronous events, and I think I've talked through the next slide already. So there is nothing that I have to say here. And so if you think about this interrupt, so in terms of handling the interrupt, what I mean by handling the interrupt is when this program discontinuity happens because of a keyboard being activated, or a divide by 0, or a system call that you make. In all of these cases, what needs to happen in the processor is exactly the same. What needs to happen in the processor? What needs to happen in the processor? What's your name? Charles, right? Right. So what is that similar to? More than that. Yeah. So that is a procedure, right? So in when you write a program, we talked about procedure calls. That's exactly what is going on, right? So from a program, you make a procedure call. What you do is you save your state, go off and do the procedure call, and after you got done with the procedure call, you come back where you left off, right? So in some sense, program discontinuities, whether it is interrupts, or whether it is trap, or whether it is exception, the semantics is very similar to a procedure call, that you're leaving what you're doing, going off and doing something else, and then coming back, right? What are the differences? Is there any difference between James, between a procedure call and this program discontinuity that we're talking about? Any difference that you can see? Anything at all? Or is it exactly the same? So first of all, think in the following sense. In a program, if I have a procedure call, is that something that you intended? That is something you intended. What about these discontinuities? Is that something that you intended? You did not, right? So it's unplanned procedure call, right? So you think of these discontinuities as unplanned procedure calls. And since it is unplanned, in a planned procedure call, you're doing certain things. You're saving the state and saving the return address, and then computing the target of the branch, going off there, executing the procedure, and then you know where to come back, right? So all of those are well orchestrated because it is a planned activity, right, making a procedure call. But here, program discontinuity is an unplanned activity, right? And therefore, we need to do, we need to sort of cover ourselves, right? And this is where the partnership comes between hardware and software, because the certain things that the hardware has to do implicitly, and certain things that the software has to do in order to help the hardware make the right decisions, and we'll see that. So this is showing you what is going on semantically. Program discontinuity, you go off, and this procedure that we're executing is what is called a handler. Okay, it is handling the program discontinuity. Okay, and that handling can be part of your program. For instance, if if it's an exception, it's something that your programmer has to be able to handle it. So, for instance, have you all written Java programs? So Java throws exceptions, right? So when it throws exceptions, you have a handler that handles that, right? And so you don't expect that to happen, but if it happens, you have to handle that, right? And similarly, and as a result of handling that exception, you may come back, or you may decide to quit, right? If the exception is a terminating condition, you may quit. So it's not guaranteed with this discontinuity that you'll actually come back to where you left off, right? It is possible that you'll come back. For instance, if you make a system call, meaning there is a trap into the operating system services that, and then it is going to bring it back to where you left off, right? And so that's the difference. There's a difference between normal procedure call and these program discontinuities. Is that clear? Is that clear? Okay. So it can happen anytime. First of all, that is one major point, is that during the execution of the program, it can happen anytime, a discontinuity, and you don't always know where to go, right? Because it depends on the type of discontinuity. That is going to determine where you're going to go, and that's the second thing. And the third thing is that once you're there, once you're over here, I have to come back here, and I have to somehow find out where to come back to, right? So this is another thing that you have to worry about. So these are all the things that we have to look at in solving this problem. So what we have to do is we have to modify the hardware a little bit. And first of all, when we have this discontinuity, right? And the discontinuity is going to result in the processor having to suspend what it is doing, and it needs to know what is this discontinuity. I said that I don't know where to go, and I need to. The processor has to find out where to go, and the way it finds that out is by having a special register in which we're going to capture the source of the discontinuity. Okay, and that register is what is called the ETR register, a new register that we're adding to the LC2200. This is internal to the processor architecture. You don't see that from the instruction set of the processor. It is internal to the processor in order to handle this discontinuity. And what is going to happen is, when you have a discontinuity, let's say that Michael's example, that you have a divide by 0. Okay, when that happens, then the hardware is going to generate a number, unique number, okay, and put that into this register. And let's say there is a trap, okay, but you made a file system call, and that results in the processor generating a trap instruction. A new unique number is going to be put into this. Or let's say Taylor pushes the keyboard, and that results in an external interrupt. A unique number is going to be put into this. Okay, so that way, now what we've done is we were doing a program execution, and suddenly there is an event that causes discontinuity, and the source of the discontinuity is registered in this register. Is that idea clear? You can see that in hardware you can actually do this, right? So it's not magic anymore. So that you can actually generate a unique number corresponding to each source of discontinuity and put it into this register internal to the processor. Okay, I want to make sure that this idea is clear, because the next thing that we're going to do is, once we have this number, then we can say that there is a table which we'll call the interrupt vector table, okay, IVT, interrupt vector table, and what this table contains is, for each one of those numbers that I'm going to generate, there is an address that I'm going to store, okay, and this address is nothing but the address of the handler that we have to go to when that particular discontinuity happens. So for instance, if the reason for the discontinuity is divide by 0, the number that I generate is 0, and when I come to this table, this contains the address of the handler in memory. So this is memory, and in memory I have handlers for all of these different kinds of discontinuities, right? So I go to this discontinuity handler if it's a divide by 0. On the other hand, suppose there is an interrupt from the keyboard, then it's going to generate a unique number that corresponds to this guy, and I'm going to jump to the handler code for the keyboard interrupt, right? So this is very simple mechanism that you can put in hardware, and this is how we solve the problem of not knowing where to go to, right? So that we have solved right now. We said that we can actually find out where we have to go to, because at the time that the discontinuity occurs, I'm going to register the type of discontinuity in a special register called ETR, and once I have that, that indexed into this table will tell me where exactly I need to go. The target of the branch is known. Is that idea clear? Okay, so that's the first part. Okay, then the other part is to do with I said that you don't know when it is going to occur, and when I say when it is going to occur, if you think about a program, let's say add, NAND, and so on. Okay, so this is your program, and it's a sequential program. A discontinuity can occur at any point, and if it happens, is it guaranteed that the discontinuity will happen exactly in between instructions? There is no guarantee. It can happen at any time. Synchronous discontinuities will happen at this point, right? So for instance, if there's a trap instruction, it's an instruction in itself, and therefore you know it is going to happen at that point. Or a divide by 0, you know it's going to happen here instead of this, but it is in this instruction. But external interrupts, you have no way of telling when it is going to happen. So it is possible that while I am executing the micro sequence for this guy, right? So this is a micro sequence. You got add 1, add 2, etc. These are all the micro sequence, and it can happen at any point, right? And the interrupt can happen at any point. And if it happens at any point, should I allow it to? Should I immediately go and listen to that interrupt? So Zoeb says that let's wait till that instruction is done. Why is that? Right. What is the problem if you allow an interrupt to be entertained in the middle of the sequence? Matt. Yeah. Well, what else can be wrong about that, Shane? Yeah. Yes. An A register. So there are internal registers, right? So the data path contains all kinds of internal registers. And now if you say that an interrupt happens in the middle of the micro sequence, then you have state that is inside the data path, and you have to save all that state. That's messy, right? Depending on the complexity of the data path, that's too messy. We don't want to do that. And instead, if we decide to take the interrupt at well-defined points, even though it is happening anytime at once, we have the ability to say when I say we, I mean the processor, has the ability to decide when to take that interrupt. Okay, it's sort of like I'm lecturing and Shane puts up a hand, right? So I can immediately stop my sentence halfway and then see what she has to say. Now that will mess me up completely, right? So instead I might say, well, I'm going to finish my thought, right, before I am going to take that question. And so that is the same thing that the processor is doing. It's saying, I know that this interrupt came in the middle of this add 1 micro state, but I'm not going to listen to it yet. I'm going to wait till this instruction is complete because it's a well-defined point. The only thing I have to worry about at this point is the externally visible registers, right? The internal registers to the data path I don't have to worry about if I'm entertaining interrupts in between instructions as opposed to internal to the instruction. Okay? So that's the first point, is that entertaining interrupts is going to happen at the end of every instruction. So what we're going to do is we're going to modify the data path slightly. So we've got the finite state machine. The finite state machine, it used to go from fetch to decode, to execute, and then back, right? So this is your normal finite state machine that is doing your instruction execution. What we're going to do is, at the end of execute, I'm going to ask the question. So there is a new line in the data path, which I'll call the interrupt line, right? So any external event or an internal event is going to assert this line that says there is an interrupt, right, or a program discontinuity, right? And I'm going to use the word interrupt and discontinuity interchangeably, but you understand that, you know, all, whether it is a trap or an exception or an external interrupt, they all have the same disruptive quality on the processor. And so basically what we're going to say is there is the interrupt line that is asserted, and when the interrupt line is asserted, then if it is not asserted, then I can simply go back to the fetch again. So that's a normal sequence of events. If there is a program discontinuity, then I'm going to go into the special state, which is called the interrupt state. Okay, and what I'm going to do here are two things. Okay, you know, Matt said that, you know, my PC may be messed up, right? So the PC is already incremented, and what was the PC pointing to? The PC was pointing to the next instruction here, right? It was pointing to this next instruction, and this is where I want to come back. If I'm going to take the interrupt, I want to come back here, right? And so what I'm going to do is, this is happening in hardware. The hardware is saying, well, I know where exactly you need to go back. I'm going to call a new register. If you go back to your LC2200 instruction set and the registers that you have, I mentioned a K0 register, which I didn't explain what that was. The purpose of that is being used by the processor implicitly to store the PC whenever there is an interrupt, right? So that's the register in which the PC is stashed away, okay? And then what it is going to do is, it is going to get the new PC and put it into this, into the program counter. Where does it get this new PC from? Where does it get the new PC from, Ron? Is it the register? It's a table, right? So the register gives you the index into the table. You go into the table, and that tells you exactly the address you want, right? So the IVT, the interrupt vector table, that contains the address that corresponds to this particular discontinuity. So you can get that, the hardware can get that, and then put it into the PC, and then go back to the fetch, right? So essentially what we've done is we've stashed away the current, the return point, and we've also computed the target, and now we're ready to go off to the handler. Okay, Matt? Yes, it's an array of addresses. Let's build on that. So who puts that who builds that array? Well, let's go back to the picture. That might help you. So who builds this array? So who writes this piece of code here? Who writes this piece of code? What do you mean by that? More than that? The OS, right? So if you think about device, these are device drivers, right? So the device drivers are things that are written by the operating system. And so if you look at this, you know, all of these are different kinds of handlers, but the authors of these handlers are different, right? The author for this handler, who is likely author of this handler? Well, there's the divide by zero exception. I talked about in Java, you have exceptions that are thrown, right? And if you throw an exception, you have to handle it. So there are certain handlers that are written by the programmer. There are certain handlers that are written by the compiler. Somebody said compiler, right? So runtime system, right? So if you have a dynamic memory allocation, right? If you do a malloc, okay? So that is going to the compiler, because runtime it is managing the heap, and so there is a piece of code that is going to do the dynamic memory allocation, right? And if it is a device driver, like a keyboard, that's something that is going to be written by the operating system. But all of these are well-defined pieces of code, and where it resides in memory, who is going to decide that? Where exactly these things are going to reside? The operating system is going to decide that, right? So what the operating system is going to do is, it is going to create this table, right? So when you boot up the operating system, the first thing that happens is that, one of the things that happens is that it is going to fill up this table saying that where are all the handlers for the different types of discontinuities that can occur in the program, Okay, once I have done that, then at runtime, if a discontinuity happens, the hardware can quickly figure that out. Okay, that was a nice lead-in. I mean, to what Matt asked this question about, who actually generates these addresses. It is done by the operating system at the beginning in setting up this IVT. Okay, everybody with me here? Okay, so that's good. So we understood this, and now if you have this picture here, you can see that as a result of the interrupt, I'm going to go off and then start executing the handler. So let's say that what I'm going to do is let's use a different color here. All the pens are over here. So I go off and start executing a handler. Okay, so this is a handler I'm going to execute, and the hope is that after executing the handler, I'm going to come back here, right? So this is my hope. Now, what can happen that spoils this happiness? Given this picture, and given what I've shown here, what can go wrong, Charles? Another exception. Suppose there's another exception. So let's say that in the middle of this guy, there is another exception, and I want to handle that too, right? And I want to come back here, and then I want to do this, and then I want to go back, right? So what is preventing me from doing that? This register, right? There's only one register, and what we've done is, for this, when we go to this handler, I've modified the K0, right? And then I go off again. I mean, in the middle of this handler, there's another exception, or interrupt, or a trap, and I go off to another handler, and now I've lost the original K0, right? So I would never be able to go back. So I can return here. That's no problem. I can return here, but I cannot go here. Okay, because I've lost my K0. Is that idea clear? Right. So this is the problem that we have with nested interrupts, and you'll see this when you implement project number 2. Is how to handle this. So how do we handle this? How do we handle this, Drew? Yeah. So anytime you want to store anything, right, you always think of the stack, right? So you can actually put things on the stack, and that's your way out of dealing with that. Shane? Yeah, so we'll come back to that. So we'll talk about where exactly the stack is. But we want to put it in the stack. That's clear. And you're asking which stack, and we'll come back to that. Okay. So right now you know that there is a stack, and so we can put it on the stack. Because if we put it on the stack, I can retrieve it later on, so I don't lose it, right? So that's good. So we can do that. And Shane, remind me your question again a little later. So what we have is the handler code. What it has to do is, it has to do certain things just like a normal procedure call. In a normal procedure call, we used to save the registers, and there we had a partnership, right? So we were trying to cheat by saying, well, let the caller do something, and let the callee do something, and maybe the caller and the callee, if they're clever, they never have to do anything, right? All of these things that we thought about. Is that possible to do that in when we have this discontinuity, Vladimir? Yeah. The caller doesn't know that there's going to be this, grabbing away of the processor from him, right? And therefore, he's unprepared for it, and therefore it is entirely on the callee, the handler, to do the saving. So what he has to do is, first of all, he has to save K0, okay, because that is telling him where to go back, right? And then he has to save the processor registers. Now there is no option. You have to save all the registers because you have no idea what the caller may be using at this point of time. Then you can execute the handler code. This is the actual work that you have to do. Whatever the source of exception, source of discontinuity, you have to do that. Shashank?
Is it possible to have another exception?
No, we'll get to that in a minute. So the minimum that you have to do is execute the code, restore the processor registers, restore K0, then we can go back to the original program, right? And so that's what we want to do. And Shashank brought up this question about what will happen if another interrupt happens before we are even done with saving this process registers. before we even say this case 0, right? This is the first instruction. Even before that, you can have that, right? And so all of these are problems that we have to solve. So Drew is calling time, so we'll stop here and think about this, and on Thursday we'll continue.